Chemical reactions. We talked earlier about chemical changes. Chemical reactions are chemical changes. And what happens in a chemical reaction is that we have one or more substances being converted into one or more different ones. So you do not have the same substances that you started with at the end. Chemical reactions involve rearrangements and exchange of atoms to make new molecules. The atoms themselves remain unchanged. So it's like building with Legos. You can take apart a structure and make a new one, but the individual Lego blocks remain exactly the same. Their size, their color, the number of them doesn't change. We use chemical equations to describe what's happening in a chemical reaction. And real simple chemical equation, we have the reactants and an arrow that points to the products. So the reactants are always on the left side with an arrow pointing to the products on the right side. One way to remember this is the reactants react to produce the products. There's a lot of information in chemical equations. They often give us the states of the reactants and products, whether they're solid, liquid, gas, or aqueous. They will give us the formulas. They'll give us the relative numbers of molecules of reactants and products. And these equations can be used to figure out what mass of butane would I need to burn to get how many grams of, 50 grams of oxygen. So they can be useful in predicting what's going to happen. The states are indicated using letters in parentheses after the chemical formulas. G for gas, L for liquid, S for solid. AQ means aqueous, and that means that the substance is dissolved in water. Let's look at the combustion of methane. Methane is one of the main components of natural gas. And when it burns, it produces carbon dioxide and water in the gas state. And it's helpful to remember that anytime something burns, it's going to combine with oxygen gas. Oxygen is one of those diatomic elements. So in a chemical equation, the formula is always O2. So we can write a chemical equation to describe this process. Here we have methane. Its formula is CH4. You're not expected to know that. It's in the gas state. It's reacting with oxygen in the gas state, and it's forming carbon dioxide in the gas state and water in the gas state. And we can get all of this information from this sentence: methane burns to produce carbon dioxide gas and gaseous water. Now, if we look at this equation, there's a problem. Here we have one carbon atom in the reactants, and in the products we have one carbon atom, and that's fine. Here we have 4 hydrogen atoms to start with, and then in the products we only have 2 hydrogen atoms. Here we're starting with 2 oxygen atoms, and now we're ending up with 3 oxygen atoms. Can oxygen atoms just appear? No, they can't. You say, well, it came from the air. Well, that's what the O2 is. It's coming from the air. This equation is not accurately describing how these substances are reacting with each other. And so it's not that the reaction is wrong, it's we need to fix our description. So as I already pointed out, there's also an issue with the hydrogens. Started with 4, ended up with 2. You can't have them just disappear. If you think building with Lego blocks, and you start with 4 of those little 2x2 red bricks, and now when you're done, there's only 2. You can't turn them into blue ones or something. They should be there. Maybe you left them on the floor, but they're still in existence. So this equation, as we have it written here, violates the law of conservation of mass. If we added up the masses of these, the atoms in these substances, it would not equal the mass of the atoms in the products, and that's a problem. So we balance the equation. And we do this by using what are called coefficients. We do not change the subscripts. So here's our equation. And now it's got a coefficient in front of oxygen. And here are pictures. Pictures are always nice. So here's methane. 1 black ball and 4 white balls. And it's reacting with 2 oxygen molecules. So that's a total of 4 red balls. And you can imagine taking these apart like Lego blocks and putting them back together. Over here, we've made carbon dioxide and water. We still have 4 red balls, 1 black one, and 4 white ones. So this obeys the law of conservation of mass. Matter is not being created or destroyed in this chemical reaction. It can't be. So we have fixed our description of the reaction to be more accurate. You cannot balance a chemical equation by changing the subscripts. You can't change that 2 on the oxygen, because that changes what the substance is, and then you're talking about a completely different reaction. Any questions yet? So we need to learn how to balance chemical equations. And this is something that I can't give you a hard and fast set of steps. That if you do this, this, and this, it'll always work out perfectly. As you probably know by now, life is not that simple. But here are some guidelines. A place to start. So the first thing is write a skeletal equation by writing the formulas for the reactants and products. You have to start with the correct formulas for reactants and products. Write those out, showing which are the reactants, which are the products. And then we're going to balance the atoms. And this part is a suggestion. So they suggest balancing the atoms that occur in more complex substances first, and always balance the atoms in compounds before atoms in pure elements. And I'll kind of explain that as we do some practice ones. Balance atoms that occur as free elements last, and then if we end up with any coefficients that are fractions, we want to get rid of those. And then check it to make sure it's balanced. So let's do an example. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon monoxide gas. So we're going to get a little practice in nomenclature here as well. So we need chemical formulas for these substances. So what's the first reactant? Silicon dioxide. What kind of a compound is that? Molecular, right? Silicon. Okay, so here's a good question. What kind of an element is silicon? It's a metalloid. We didn't talk about metalloids when we talked about nomenclature. I've not seen this written in a book, but this seems to follow the pattern. If you look at the metalloid and see which side of the line is it on the metal side or the non-metal side? This one's on the non-metal side, silicon is. It's on the same side of the line. So then we're going to treat it as a non-metal when we name things. If you see a metalloid that's on the metal side, then you're going to name that compound as if it were ionic. That, like I said, I haven't seen it written down, but it seems to work. So silicon dioxide, SiO2. And what's the state for that? It's a solid. And that's going to react with what? Solid carbon. Oh, that's kind of small. So that's an element. Is carbon a diatomic element? No. Horses need oats for clear brown eyes. So it's not. So it'll just be C. And that's a solid. And then we put an arrow. Notice I'm leaving some space here for a coefficient. I don't know why I'm getting that thing in the middle of my screen. We'll ignore it. To produce solid silicon carbide. What'd they do that for? So silicon carbide. Well, from the rules, what kind of a compound is that? Be molecular, right? There's no numerical prefixes in there, so we're going to assume that it's SiC. Just silicon and carbide, because if it was like dicarbide or tricarbide, they would have put something like that in there. So the absence of mono, we'll assume it's 1. That's a solid and carbon monoxide gas. So that's CO, and that's a gas. That's the first thing, is to write down all the formulas. If you go about balancing your equation and it looks like it's just going to be completely impossible, check your formulas. If one of the formulas is wrong, it may be impossible to balance the equation. Okay, so now we just start balancing. This is called balancing by inspection. So it talked about balancing elements in the most complicated compounds first. I actually find that a lot of times if you just go left to right, it seems to work pretty well. So start with the first one. Start with silicon. The one thing you want to leave for the end is this carbon. Because if you get a coefficient on here and you mess around all these things and then you finish up with him, when you change a coefficient on an element, it's not going to mess up anything else. And so that's why you leave the elements for last. If you start balancing and things start to get ugly, start over with somebody else. And that seems to be my best advice. So let's look at silicon. And we ask ourselves, well, how many SIs are on the left side of the arrow? 1. Okay. And how many SIs are on the right side of the arrow? 1. Cool. No problem there. How about O2? O2. I just gave it away. There's 2 oxygens. 2 oxygens here. There's none in here. So a total of 2 oxygens. And then over here, how many oxygens do we have?
1.
Just 1. So how can we fix that? We need to put a coefficient in front of the compound that has oxygen in it. So we'll put a 2 here. It's tempting sometimes to write a subscript here that would take care of the problem, but now you've changed the reaction. You can't do that. So now we've got 2 carbons. 2 oxygens. Did that mess up the silicons? No, it didn't affect them at all. So that one's still okay. So we've got 2 oxygens, 2 oxygens. Now we need to look at carbon. So on this left side we have 1, and how many carbons do we have on the right side? 3. There's 2 over here and 1 here, a total of 3. So we need there to be 3 over here. So we'll just write a 3 there. And then you should go through and double check that it's the right number on each side. Any questions? That was kind of a simple one. Let's do another one. Write a balanced equation for the combustion of gaseous ethane. They give you the formula because wouldn't expect you to remember that. It's a minority compound of natural gas. Combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. It's a lot of gases. So again, we start with the formulas for the compounds. So the first one is C2H6, and we're told that's a gas. Now, those state symbols, if the instructions given specifically include state symbols, then you have to. So this one doesn't say we have to include state symbols, but since they're giving us all of the information, we're going to practice. State symbols are something we put in if they're needed and we leave out if they're not. So this is combustion. Combines with gaseous oxygen. So it's combining with oxygen. Is oxygen a diatomic element? Yeah. So that's O2. And forming carbon dioxide. So that's CO2. and water, H2O. So I'm going to show you a little bit different way of balancing, or maybe a more visual way of keeping track of what's going on. That last one was pretty simple, and so we kind of just did it in our head. Sometimes things get a little more complicated. Go ahead and try it in your head, and if you're like, oh wait, this isn't going well, then maybe you need to write some stuff down. So this is what I've found helpful to a lot of students. Draw a vertical line through that arrow to divide the two sides. And then on the left, make a list of the elements that you have in the whole thing. So we've got carbons, we've got hydrogens, and we've got oxygens. And then just go across, and under each formula, just make an accounting of what you've got in there. So C2H6, we've got 2 carbons, we've got 6 hydrogens, and we've got no oxygens. And over here, we've got no carbons, no hydrogens, 2 oxygens. That's something in my eye. It's probably soot. Over here, CO2, there's 1 carbon, no hydrogens, 2 oxygens, and then this guy, no carbons, 2 hydrogens, and 1 oxygen. Now we've got a little more to look at here. And then I typically just start with the top one. So I look, the total carbons on the left side is 2, and the total carbons on the right side is 1. So I need to put a 2 in front of this guy so that I can have 2 carbons. And so that changes this one. It also changes that one. Multiplies it by 2. So now I've got 4 oxygens down there. I'm just keeping track. I'm not balancing that one yet, but I'm just keeping track. Next element is hydrogen. So we have 6 plus 0 and 0 plus 2. Well, we need this to be a 6. And so we're going to multiply that by 3. So we'll put 3 up here. So 3 water molecules will give us 3 times 2, 6 hydrogens. And then we'll end up with 3 oxygens. And that did not change the carbons, so the carbons are okay. Because sometimes when you fix one, you mess up another one. You have to go back and adjust. Now we look at the bottom one, oxygen. And this works out well for being last because oxygen's by itself. So here we have 0 plus 2. And we've got 4 plus 3. So we have 7 on the right side and 2 on the left side. So how do we multiply 2 to get 7? We can use a fraction. We could do 3.5 or we could do 7 halves. So that's one way. Then we're going to end up with a fraction we need to clear. So let's go ahead and do that. So if we put 7 halves, wait, that's not the color I wanted. I don't know what color I wanted, but if we put 7 halves here, 7 halves times 2 will give us 7 oxygens, and 7 oxygens on the right. So we're balanced. And this is what that list of instructions was talking about, clear the fractions. So now you can go through and check that everything is balanced, but we don't like fractional coefficients. So the way to get rid of 7 halves is to multiply everything by 2. So you're going to go through and you're going to have a 2 here, and you're going to multiply this by 2, and that 2 will go away. This is going to become a 4, and this is going to become a 6. And then you should check that it's balanced. So that's one way to take care of something like this. Let's do it the other way. I wish I could rewind my life sometimes. So here, these oxygens are coming in pairs, and we need 7, an odd number on the other side. This is what I call the odd-even problem. The way you get around this is by doubling everything, because if you double an odd number, it becomes an even number. So in this approach, what you do is you just take all of your coefficients and you multiply by 2. So I'm going to put a 2 here. That becomes a 4 and a 12. This is the one I'm adjusting, so I'm going to leave him alone. This becomes a 4, so that's a 4, and this one's an 8. And this is going to be a 6. So this becomes 12 and 6. I multiplied everything but this oxygen by 2. Now go ahead and check. 4 plus 0, 4 plus 0. Carbons are still balanced. 12 plus 0, 0 plus 12. Hydrogens are still balanced. Now I've got these oxygens coming in pairs, and on the right side, 8 plus 6 is 14. I'm looking for 14. Well, that's an even number. So then I can say, oh, well, I need 7 of these. And then that works. So that's, if you don't like fractions, that's a way to get around having fractions. Any questions? Do another one. Write a balanced equation for the reaction between aqueous lead-2 nitrate and aqueous potassium chloride to form solid lead-2 chloride and aqueous potassium nitrate. Again, we need formulas. Lead-2 nitrate. What's the formula for that? PbNO3, 2. Lead-2 means it has a +2 charge. Nitrate has a -1 charge, so we need 2 of them to balance the charge on the lead. And it says that's aqueous. And then potassium chloride, what's the formula for that? KCl, another ionic compound. Potassium has a +1 charge, and chloride has a -1 charge. I'm trying to move these guys over. Come on. I'm having technical issues here. Okay. Pause. Okay, I just had to move those guys over. Products, lead-2 chloride. What's the formula for that going to be? PbCl2. So the way we're thinking about that, Pb2 is lead-2 is Pb2 plus, and chloride is Cl minus, and so then we need PbCl2. And then aqueous potassium nitrate, that's going to be KNO3. This is one of those situations where you sometimes leave the state symbols out until the end because they get in the way. Okay. Yes, to form solid lead chloride. Thank you. I missed that. So precipitate, yep. Yeah, because actually if they both were aqueous, it wouldn't be considered a reaction. Thank you for catching that. Any other questions? So all of these are ionic compounds. And we've got a polyatomic ion in here, nitrate. So here's nitrate in the reactants and nitrate in the products. We can actually treat that as a unit because it's not coming apart. And so we can balance nitrate as an ion instead of looking at nitrogen and oxygen separately. So that's what I'm going to do. You can also do them separately, but I think it's easier to just treat it as a lump. So how many PBs do we have on the left side of the arrow? 1. And how many on the right side? 1. Okay, that's cool. How many nitrates do we have on the left side? 2. And how many on the right side? 1. So what we need to do is put a 2 here so that we'll have 2 nitrates. That didn't change the lead, so we don't have to revisit him. Let's go on to the next compound, KCl. How many Ks? 1. And how many Ks on this side? 2. So we need to put a coefficient here. So I have 2 potassiums and 2 potassiums. Now, putting the 2 here did not mess up the lead or the nitrate, right? And so now we can go on and we see 2 chlorines and 2 chlorines. In these ionic reactions, a lot of times that last ion will take care of itself. Any questions? This is one of those things that tends to look really easy when I do it on the board, and then when you try to do it yourself, you're like, oh, wait a minute. Any questions?